So that was quiz 2. We've only got 3 in the semester. Of course, there's still lots of points on the table between the next exam and the final and the project. So let's go through these announcements here. Oh, no, class on Thursday is not online. That's not true. I think that's from last semester. Sorry to get your hopes up. You've got to see my ugly face again on Thursday. Psych. All right. But on Thursday, so good news, bad news. Good news, we're having class. Bad news, you've got a homework assignment due. It's a relatively quick one. You know, the first half of any one of these new chapters is usually kind of the light material, and I think that's what this chapter 12 first set of questions is related to. Now, I've gone through the demand estimation, all of the submissions that you made for that, and my comments and your scores are online. If you have any questions or uncertainties about the things that I mentioned in my feedback, I'd be glad to speak with you during my office hours. Sometimes I wasn't able to be as generous with the praise as I wanted to be because, you know, I've got 20-something of these to score, and I think the most valuable thing for you to hear is where I think the mistakes are. And so I think a lot of you did a really nice job, and if I'd had more time and my fingers weren't already sore, maybe I would have gone into more detail about how impressed I am, and you did a great job, and keep up the good work, you know, like kind of a feel-good pat on the back. And there were a lot of those that honestly merited that kind of treatment, but instead the more valuable thing for you to hear is if there are mistakes, what they might be. So if you have any questions on the feedback I gave you, please let me know. The next phase of your project is due on a week from today. Now, it looks like Bentley has changed the license manager that they use for their software. They now have this tool called Connection Client, and I'm not the biggest fan because I don't like it when programs run in the background constantly without really needing to be there, and it seems like that's what Bentley does. You'll just have to have it on your computer for a month or so, then you can uninstall it, and it won't constantly be running in the system tray. I find it irritating, but just to let you know, get an early start installing the software if you don't already have it installed, because the activation is a little bit strange. I went through it yesterday when I had a student question, and I'd never seen what was coming up. I hadn't seen it before, so I uninstalled the software and reinstalled it myself, and it did work, but it was a little confusing, like where to click and how to make it run. So that's why I sent you a link yesterday with some instructions from Bentley on what to do there. I'm going to show you an example of what a good annotated map looks like. And so what you need to submit a week from today are 2 PDF files, or I guess a single PDF file that has 2 pages. One map that shows your system at the full demand, so the design flow rate, and then one annotated map that shows your system at 0 flow. So I'll show you what I mean about that. We're going to continue talking about open channel flow today, going into some more of the foundation topics that are required to be able to predict what's the depth of flow when conditions aren't steady and uniform. Manning's equation is great, but it has limited applicability because for it really to apply, then that means that you have to have a prismatic channel that's really long and everything's become quiescent and steady and there aren't any variations and there aren't any disturbances, and that's very rarely the case. And so we need more sophisticated tools to be able to predict what the depth might be in other conditions beside that very unlikely uniform steady flow. Any questions before I show you these maps for the design project? Yes?
Is that the same software that we downloaded last semester?
It is.
There's no other, is it the current version, or should we look at updating?
Well, I think some of you may have installed version 8 last semester. They're on version 10 now, and in fact it's even a different version of version 10 than they had last fall. So the current version 10 has a release date of December 2018. I don't know that it necessarily adds any new functionality that you have to have access to. But I mean, if you've got operational water gems and you're happy with it, then that's fine. Not necessary to upgrade. All right, phase 1 of the project, you answered the question, how much water? You were analyzing the population, you were analyzing the industry, you were looking at climatic conditions, rainfall, evaporation, vegetative growth. You looked at all that thing, and you're trying to define what the flow rate is going to be coming out of certain junctions in the network. This next phase of the project answers a different question. It says, what size of the pipe is required? And specifically, what you're going to be doing is optimizing the pipe size to try and find the pipe size that's just barely big enough to satisfy the needs. Now, a secondary question that's related to this is where to put the reservoir, how high on the hill, because where you put the reservoir is going to affect the pipe size that's required. And I don't want to say too much there because it's kind of a learning opportunity to play around with different locations on the hill and see what the implications are for pressure in your network. Now, I've already told you before that your network at the design flow should not go any lower than 240 kilopascals, and under static conditions, meaning that there's no demand, the pressure should never be any higher than 850, any place in the network. Now, your network is on a sloped hillside, and so different points in the network are going to be more prone to high pressures, and other locations are going to be prone to the lower pressures because of the elevation gradient that's there. Now, it's easy to get a pipe network that will satisfy the requirements if all of the pipes are oversized. You'll still have good pressure, but of course the cost is too high. So what you're trying to do is push the boundaries to make the pipes progressively smaller and smaller, and that minimizes the cost, but then the cost in terms of the hydraulic cost rather than the economic cost. The hydraulic cost is that the pressure keeps decreasing. And so you want to bump up against this limit of 240 as much as possible. Because remember, what you're designing for, this worst case scenario, is that the football stadium's full, the mall is full, the food factory's going, they're irrigating at the golf course, there's a fire, residential peak demands, kind of everything bad is happening all at once. And that's likely to occur in a 30-year period, maybe for one afternoon. It's not going to happen really often. So your pressure in the network for these people would be noticeably low that day. But that's the extreme case, and most of the time the pressures would vary in a much narrower window. So ordinarily, on a day-to-day basis, you wouldn't want the pressure to swing between 240 and 850 every day of the week. I mean, that would be really not just annoying, but it could cause physical damage to the infrastructure if it swung back and forth that often, that much. But on the peak day, it's okay for it to dip as low as 240. So makes the pipes just barely big enough. That's the essence of iterative design. Now, there are a couple of resources here that if you maybe have lost touch with the very brief demo we had in lab last semester and you want a refresher on how to click on the buttons and how to type in pipe data and that sort of thing, I have a couple of YouTube videos there, and so you know, these slides are available on MU Online, so you don't have to necessarily write down this link. You can just click on it in the notes. Nowadays, I think that most programs have a built-in PDF printer, but if your computer doesn't, you can have a free open source PDF printer so that you can go straight from the program to printing PDF files. And so PDF Creator is a good resource for that. This is what, and this is a good example of what you need to turn in on a week from today. Now, this is from a few semesters ago, and one of the differences between then and now is back then I didn't give students the flexibility to locate the pipes wherever they want. And so back in this day, the students were required to follow a certain route for their pipe networks. But now you're not. So for example, see this junction J? There's no outflow at junction J, so the water doesn't necessarily even need to be there. So maybe it would make more sense to have the water go straight from K, which is the hospital, over here to I, the housing project, because you're going to minimize the distance if you go in a straight line rather than going in a less direct route. So the point I'm making is that part of your optimization isn't just the pipe sizing, but it's finding out what's the lowest number of linear meters of pipeline distance that's needed. So taking as another example here, let's look at junction E. 33 liters per second is coming out of junction E. You can see that they've annotated the pressure, 278 kilopascals, and so they're above the limit. That looks good. But do you notice that water is coming towards junction E from two directions? It's coming from F, and it's also coming from D. So that's a little bit redundant. We could probably eliminate this entire section of pipe from F to E. Only 5 liters per second is going through there. So if I just cut that entire pipe out, then the needed water could come through this pipe instead. So look for little tweaks like that. Minimize the total length of pipe that you're using. So annotation means notes that indicate characteristics. So the pipe location is identified by the lines, and you should use a naming system like shown here, junction A, junction B. I think those are all those letters given in the map that I gave you, right? The junctions have letters on them. So use that same naming system for the junction annotation. The diameters should be listed here. So you can see that they've annotated for each pipe the flow rate that's going through it, the length of the pipe, and the diameter. So those are the pipe annotations. And for the junction annotations, there's the name, the flow rate that's coming out where applicable. Now, not every junction has flow rates coming out. This one does. And then the pressure. And it looks like this is the system at the design flow. Otherwise, I'd expect the pressures to be a lot closer to 850. At least somewhere in the network, they should be closer to 850. So this is, I guess the other clue that this is not the zero flow condition is that there's all these outflows at the junctions that are identified. So that's the other clue. The other thing to annotate is the reservoir location and the elevation at that spot. So how long this pipe is going to correspond to where you want it. And I see the map. Can I borrow this for just a second? So if you are doing your calculations, you decide that you want to see what's going to happen with the reservoir up to 275 meters. So then that means you have to measure with the ruler how far is it from A to the location at 275 meters on the contour map. And so you measure that and you say, oh, maybe it's 550 meters. And so now in the network, you're going to have a 550 meter pipe segment so that you accurately represent the physical length of that pipe. It doesn't really matter. These aren't steep enough that you'd see an appreciable distance between the horizontal distance and the physical length of the pipe. So you can prove that to yourself, but I don't think you necessarily need to distinguish between the two. The other thing I wanted to point out is, what was I about to say? I've lost it. Another senior moment. I'm occasionally getting those. All right? Yeah. All right. Are there any other questions about this map? All right. So you'd have another one where you're analyzing at the zero flow condition. So what you'll probably want to do is save the file, save it like at the design flow rate, and then save another copy of the project at zero flow rate. Because you're going to have to manually go in, and for each of those locations where there's a demand, you're going to have to manually go in and say zero demand and then recalculate the pressures. And so you maybe will want to have two different versions, the zero demand version and the design flow version. Now, the tricky thing can be if you start to make changes, you have to remember to make changes to both systems, because you wouldn't want to have one system where the pipe is 400 millimeters and another system where the pipe is 500 millimeters. That would be a real issue. One last thing. is that if you're bringing up the image file in the background, you no longer have to use user-defined length. Now you can use scaled lengths, which is kind of convenient, so that where you click is actually implying a distance and a location in the background memory of water gems. So that if 1 meter is 1 pixel, and that's the intention with the file that I provided you, the image file that you can import in the background, 1 pixel is 1 meter. So it knows when you go from J to H, the certain distance in pixels between those 2 points implies the physical distance in the real world. All right, so now what we're going to talk about is some more open channel flow considerations. And you maybe remember that we've already talked about total energy. And total energy is another word for the energy grade line. And remember that there are 3 terms to energy grade line. The 3 terms are the elevation above some datum, and so that's Z, the depth of flow, which is Y, and then the velocity head. The specific energy is different from total energy because it doesn't include the delta Z term, the elevation above some datum. It's called specific energy because what we're talking about is the energy relative to the channel bottom at a certain location. And so we have water that's flowing downhill, and what we're doing is we're measuring the depth of the water relative to the channel bottom at that spot. So here for specific energy, you see we still have the depth and we've got the velocity head, but there's no Z term in specific energy. So to illustrate how we use specific energy and what it means, let's consider a rectangular channel that has a bottom width of 4 meters and some unknown depth. Now, of course, the flow rate Q is going to be the velocity times the cross-sectional area. So let's say that we know we're going to pour a certain amount of water down this channel. We're going to have this channel convey 10 cubic meters per second. And so now think about all of the different combinations that could occur of velocity and depth. Like for instance, what you could have is you could have a really shallow depth, but the water's moving fast at a high velocity. And so you'd have a high V, and the cross-sectional area would be relatively low. And that would be characteristic of a pretty steep slope. That's how you get a fast velocity, and a shallow depth is a steep slope. At the other end of the spectrum, if the slope was relatively mild, then that would mean the depth would have to be taller, and the velocity of flow would be less. Any questions so far? Here's a table that just kind of illustrates a range of extremes. So at the one end, here is a high velocity for the certain flow rate. And so if we know that the cross-sectional area is Q divided by V, then the cross-sectional area here would be 1 for this top row. The depth, A divided by 4, just because we know that the cross-sectional area is going to be this bottom width of 4 times Y. So if we just rearrange to solve in terms of the depth Y, then it's going to be whatever the area is divided by 4. And so for each one of these different combinations, we could calculate the specific energy. And by the way, I've done that thing to the velocity head that sometimes we do. Now here on this page, rather than saying V squared divided by 2G, we can also express the velocity head as Q squared divided by 2GA squared. We did that sometimes in closed conduit flow, and we can do the same thing in open channel flow. All right, so take, for example, if the velocity is 10, then that means the cross-sectional area is 1, and the depth would then be 0.25, and we could even calculate the specific energy. So the specific energy would be this depth of 0.25, and then we'd need to multiply Q squared divided by 2GA squared. Now you'd have a pretty high specific energy, at the this top row, and most of the specific energy is coming from the velocity head. Do you see how that's the case? That the velocity head is mostly coming from, the energy is mostly coming from the velocity head, because if the energy is two things, it's the depth and the velocity head. You can see that the specific energy, when the depth is really shallow, is only 0.25 meters from the depth, but 5 meters of the specific energy is coming from the velocity head, because E is those two things. And so most of it must be in the form of velocity head. At the other extreme, if we consider when the velocity is really slow moving, if the velocity is 1 meter per second, then you'll see that most of the specific energy is from the depth. 2.5 meters of the 2.55 meters is from the depth. Now, there is this special location where we've got the minimum amount of specific energy. So the specific energy is high, it's decreasing, and then it starts to increase again. So it's decreasing as we're going down because the velocity is decreasing. And the velocity is decreasing at a rate that's faster than the depth is increasing. That's why the specific energy is declining. But then the specific energy comes to some minimum point, and it begins to go back up again. And this point of minimum specific energy is kind of a special location, and it corresponds to critical flow conditions. And the definition of critical flow is it's the most efficient, from an energy standpoint, the most efficient way to convey a certain flow rate. And the way to think about it is, in each one of these cases, we're trying to get 10 cubic meters per second down a channel. How much energy does it require to get that flow down the channel? If you want to have 10 cubic meters per second going down the channel at a really high velocity, then there has to be 5.3 meters of energy there. So it's using a lot of energy to have this flow condition, and likewise, it requires a relatively high amount of energy to have this tall water depth of 2.5 meters. But from the standpoint of minimizing specific energy, the most efficient depth would be a depth of 0.861 meters. Now, we have a formula that's going to allow us to calculate what is this magical depth, but I want to point out that one way you can identify the critical depth is through this graphical approach, where you just have, for a certain flow rate, lots of different combinations of velocity and depth, and then you calculate the specific energy from those velocity and depths. So here's that graphical approach visualized. What we're taking from the table here is flow depth versus flow velocity. And so of the two figures that are going to be on this page, this is the less interesting of the two, but still there's something going on here. There is the trend that as the depth gets deeper, the flow velocity is lower. And of course, the reasoning there is that if you have a big velocity, you have to have a shallow depth in order to still have the same 10 cubic meters per second. And so it's the product of velocity and area that gives you the flow rate. But what's more interesting than graphing this, really the kind of new insight that's going to allow us to solve a lot of different problems, is that we could graph the specific energy. Instead of graphing just the velocity, what if we graph the energy instead? So that's what this figure is showing. Is it's saying, let's put the depth of flow on the vertical axis, and then the specific energy that corresponds to that depth of flow on the horizontal axis. Okay, so if we go back to the underlying data, you'll see that there were two different specific energies corresponding to two different depths of flow corresponding to the same specific energy. So take, for instance, around 2.5. So there's a 2.5 meters of energy in the lower range where you have low velocity and high depth. But then there's another crossover point in between these two where you again have the same 2.5 meters of specific energy, but that's where the velocity was much higher and the depth of flow is much lower. So what we've done is we've taken this E column and the depth column and have graphed it in this way. And the critical point of the lowest specific energy, we can reflect that point over to the vertical axis, and that's the same depth, the critical depth of 0.861 meters in this case. So that corresponds to the minimum specific energy for a certain flow rate. Now it's for a certain flow rate and a certain channel configuration. It was, remember, this is a 4-meter wide channel. If it was any other channel geometry, then it'd be a completely different figure. Or if it was any different flow rate, then the figure would be changed as well. Now, the thing that controls whether the flow is going to be supercritical or subcritical is the slope of the channel predominantly. I mean, all of the geometric parameters play a role, but there's a region of this graph, any flow depth that's below the critical depth, we call this region supercritical flow. And I know that's going to be at first counterintuitive because you'd think, well, if it's below a line, why is that supercritical? So the red dot, this red dotted line, that is the depth that corresponds to critical depth. And if any of the depths are less than that, then that means that the velocity is faster. And so this is the region of the figure that's supercritical, and above the line, what that means is that the water is moving slowly because it has a relatively higher depth. So for the slower moving water, then you have subcritical conditions above the line. And we'll get into all of that, but you know, what actually determines whether the flow depth is shallow or deep and whether the velocity is fast or slow, slope is the main factor that controls it for a given section shape.
Is the critical depth in the box, or is it anywhere below that? Or I'm sorry, where it's supercritical?
Yeah.
Anywhere below it?
It would be any of the depths below it.
Oh.
Mm-hmm. Yeah. So along this line is the specific energy that corresponds to various depths. And so if you had a flow depth of 0.5 meters, then you could go over and say, well, the specific energy at 0.5 meters is, it looks like, around 2 meters of energy. The other thing that's a really big idea you're going to hear over and over through the coming lectures is the idea of alternate depths. These are two depths that have the same amount of specific energy. And so there are two depths that have the same specific energy, for example, of 2 meters. So it looks like if you have 2 meters of energy, the flow might be going, looks like maybe 0.45 meters of depth. That would be the supercritical depth associated with a specific energy of 0.2 meters. And then if you go back through the other intercept of that figure, it looks like there's also a flow depth of around 1.9 meters for the same specific energy. And these alternate depths come into play during hydraulic jumps. It's one of the main places that we have to know about alternate depths, is that sometimes the water is moving much faster than it should. And it can't be supported. The flow conditions, like when the water comes down the face of a spillway in a dam, well, obviously once the water comes off of that dam, it's not going to continue to have the same velocity because it was accelerating and speeding up as the water went down the face of that dam. And so it gains all of this energy, but now it's at a really shallow depth as the water comes off of the dam, and it can't stay at that shallow depth for very long when it enters a channel that's a relatively mild slope. So it has to go through a transition and jump from the supercritical depth up to the alternate subcritical depth for the same amount of specific energy. So one of the features that often get designed downstream of the dam spillway is some sort of like a stilling basin to absorb the energy that occurs after a hydraulic jump. Another illustration of the features that would cause a hydraulic jump is when water is flowing under a gate. And so water underflow from a gate can cause a hydraulic jump, and we'll walk down to the lab in a couple of weeks and look at the hydraulic jumps in the flume. And that's how we induce a hydraulic jump in the lab, is through an underflow gate. The idea is that if you know, if you can graph this specific energy curve, then you can predict what depth the water is going to jump up to after it goes through the hydraulic jump. It's important to be able to predict what the alternate depth is going to be. So different ways to classify flow. We've talked about how flow can be uniform, non-uniform, steady, unsteady, turbulent, laminar. So critical and subcritical is another way to classify flow regime. And when the depth of flow is greater than the critical depth, then that's when the conditions are subcritical. And when the depth is less than the critical depth, that's when the flow conditions are supercritical. And sometimes people get it confused because it's not necessarily the depth that is what the name is based on, but it's the velocity that the name is based on. And so subcritical corresponds to the flow conditions when the water velocity is slow. There are some geometric parameters that we can calculate. The top width at critical conditions is B sub C. And you can see that when you have a rectangular geometry like this, then the bottom width and the top width are going to be the same. But if you have trapezoidal geometry, then this top width is going to depend on how deep the water is and then what are the side slope characteristics. And the reason why I mention this top width is that one of the formulas that we can use to calculate the Froude number is shown here. And you've already seen this one, I think. But for a trapezoidal geometry, then it's easier to use this equation on the right, where you've got the flow rate, the top width, gravitational acceleration, and then the cross-sectional area. So this is the Froude number squared. And the reason why it's important to know the Froude number is that if your Froude number is less than 1, that corresponds to subcritical conditions, and greater than 1 is when you've got supercritical flow. Hydraulic depth is usually assigned D in your book. Some of the other references, I think including the FE manual, calls it Y sub H. And what that is it's the ratio of the cross-sectional area to the top width. And the hydraulic depth of a rectangular channel, now think about this now. If you've got the cross-sectional area is B times Y, and then you're dividing that by B, then the hydraulic depth of a rectangular channel is just going to be Y. There's a special case where if you have a very wide channel, and by very wide, that actually has a technical definition. What we're going to say this semester is that a very wide channel is one where the width is more than 20 times greater than the depth. So if the width is more than 20 times greater than the depth, then it doesn't matter if it's trapezoidal or rectangular, then the hydraulic depth is just also equal to Y. And the reason why is that if it's very, very wide, then the effect of any side distance is mitigated. So if it's trapezoidal but extremely wide, then those side triangles don't contribute much cross-sectional area. And the cross-sectional area is mostly the rectangular portion of the channel. So there are a couple of special simplified versions of these formulas that we're going to go through in the coming lectures that are only applicable if you have a very wide channel. All right, so I'd like you to get some practice diagnosing the flow regime here. So let's say that we have this same 4-meter wide channel, and we've got 10 cubic meters per second going through it. So what is the Froude number when you've got a depth of 0.25 meters? And also, what is the Froude number when you've got a depth of 1.25 meters? So what we're trying to determine here is the flow conditions supercritical or subcritical for each of these depths. Let's not solve it using the graph, though. Let's just go straight to the Froude number. It says to solve it both ways. Because the quiz put us a little behind on time, we'll just do the Froude number. I guess we don't actually have to create the graph. We could just look at the graph and use it to diagnose both of these cases. So depth of 0.25. If we use this vertical axis, 0.25 is less than the critical depth. We can see that the minimum specific energy has this depth of about 0.86. So if the depth is below that minimum point, then this is the supercritical range. And so for this first depth of 0.25, conditions are supercritical. And we can confirm that by calculating the Froude number. So here's the Froude number for that first one. If the flow rate is 10 and the depth is 0.25, we can calculate the cross-sectional area and find the velocity. So the velocity is 10 meters per second. And so here is the flow rate squared times the top width of 4 divided by g times area to the third power, and then we have to take the square root of everything. So since the Froude number is greater than 1, that means that this depth of 0.25 is going to yield supercritical conditions. So supercritical is that one. And then what about looking at the graph for this depth of 1.25? So 1.25 is greater than the point that's associated with minimum specific energy. So it's in the subcritical range. And we can verify that by calculating the Froude number. So the Froude number when we've got the depth of 1.25. So that means the cross-sectional area is going to be 5. Put that area into the same Froude number equation, and it should be a Froude number of 0.571. So that's supercritical. Sorry. This one was supercritical. This one is subcritical. All right. So supercritical is when the Froude is more than 1. Subcritical is when the Froude is less than 1. And we can create a figure from it. We can calculate the Froude number. Any questions about this example? All right. Alternate depths are situations where the same amount of specific energy yields 2 different depths of flow. And so if you draw a vertical line from any particular specific energy and you cross the graph in 2 locations, then that means that there's 2 different flow depths that could occur. And so if the depth is 0.5 meters, you can solve for the specific energy that goes along with that depth just by, from the graph, going over, intersecting. The other way to find the specific energy is just to substitute in the depth of 0.5 here, and then finding out what would be the cross-sectional area for this width of 4 and the depth of 0.5. So you put in the cross-sectional area, and so you're finding both the velocity head and the depth term for specific energy. And to solve for the alternate depth, what we would do here is we would find out the total specific energy at one of the depths, and then we'll find the amount of specific energy being the same for the other depth. Does anybody have a marker? There isn't one here in the classroom, but I can usually count on at least one of you guys to have it. Thank you very much. All right, so let me do this one on the whiteboard. Thank you. If we have a depth of, so y is 0.5 meters, then we know specific energy E is the depth plus q squared divided by 2g a squared. And we're going to consider this case of Q is 10 cubic meters per second. And so what that means is that the specific energy is 0.5 meters. And that first part is just the depth term. And then 10 cubic meters per second squared divided by 2g, which is 9.81. And then the cross-sectional area. And the cross-sectional area is going to be whatever the depth is times 4 meters. And so if we're doing this for a depth of 0.5, then area is 0.5 times the width of 4. So the area is 2. Okay, so the area is 2, and we're squaring it from the formula. So the total specific energy is 1.774 meters. So that's how much specific energy there is when the depth is 0.5 meters. So let's look over here. 0.5 corresponds to 1.774. Now to find the alternate depth, what we're trying to find out is what is this other crossover point of the same curve. And what we can do is we can say that 1.774 meters is y plus 100 divided by 2 times 9.81 times 4y squared. So we're putting that in terms of the unknown depth. This other unknown depth that can give you the same amount of energy. Okay, so y is the unknown depth. We still know that the flow rate is 10, so 10 squared divided by 2g, and then the cross-sectional area is going to be 4 times whatever the depth is, squared. So we can rearrange this. This is going to be a cubic equation. So we're going to multiply each term by y squared. And so that's 1.774 y squared is equal to y cubed plus 0.3186 divided by, this whole term, this last one, is the same thing as 0.3186 divided by y squared. So if we just have the 100 divided by 2 times 9.81 times 4 squared. So that cubic equation then is plus 0.3186. So there's going to be multiple roots to solve this equation. If we just rearrange it, it's y cubed minus 1.774 y squared plus 0.3186 is equal to 0. And if you put it into your calculator, what you'll find is that the three roots of this, one of them is negative 0.3842. Another one of the roots is the depth that we already knew, 0.50 meters. But then another one of the roots is the depth that we're looking for, 1.658 meters. And so that is the alternate depth, 1.658 meters. You could solve it numerically using the spreadsheet, but you can also solve it by finding the roots of that cubic equation. Any questions about alternate depths? One thing that we didn't account for was any sort of energy losses as the water goes from a transition from a supercritical to a subcritical depth. And in a hydraulic jump, like in reality, when the water goes from a supercritical depth to a subcritical depth, there is a lot of turbulence and quite a bit of energy is lost. We will account for and demonstrate those energy losses in the future. But just looking at the theory behind specific energy and alternate depths, we haven't yet accounted for any of those losses. Critical conditions, remember, correspond to the minimum amount of energy to convey a certain flow rate through a channel. And so it's where you have minimum specific energy. That means that if you look at this curve, there isn't any slope when you're at the minimum point. It's the vertical, completely vertical conditions. It's not sloped sideways like in the subcritical zone or in the supercritical zone. So this is the definition of specific energy. It's just the energy relative to the channel bottom at a given location. And if we take the derivative of that with respect to y on both sides, then this is where the Froude number equation comes from, where we're saying that the Froude number is equal to 1 at critical conditions. So the flow rate squared times the top width divided by g times a to the third power is equal to 1 at critical conditions. So if we rearrange that, so this was 1 on the right side, and we rearrange that so that now under critical conditions, if we want to find the critical depth, then regardless of the cross-sectional shape, it can be for a trapezoidal geometry or a half circle or a triangular geometry, this can always be used to tell you what's the critical depth. So just as an example, if you want to find the critical depth for a rectangular channel where the flow rate is 10 cubic meters per second and the channel width is going to be 4. This is that same rectangular channel that we've been talking about today. We can find the critical depth using this formula. Just by substituting in, okay, so it's q squared divided by g is equal to, now the cross-sectional area, if the width of the channel is 4 and the unknown depth is y sub c, so on the right hand side of the equation it would be 4 times yc cubed, and then it's going to be divided by b sub c. So b sub c is the channel width at the critical conditions, and the channel width is 4. So just substitute the 4 in there, and what that leads us to is that the y sub c is b sub c q squared divided by g to the 1/3 power, and then we multiply that by 1/4. So the critical depth is going to be 4 meters times 100, because the q was 10, divided by 9.81 to the 1/3 power, and then times 1/4, so 0.86 meters. That is the full-blown equation for it, but here is a simplified way to find the critical depth only if you have a rectangular channel. So if you have a rectangular channel, meaning that the top width and the bottom width are the same, then what you can do is you can calculate something known as the flow per unit width. That's what the lowercase q means, is it means the overall flow rate q divided by the channel width. And this formula can be used to find the critical depth only in a rectangular channel cross-section. So with the example that we've just been looking at, where the flow rate was the uppercase Q is 10 cubic meters per second, and the channel width B is 4 meters. Then lowercase q is Q divided by B. So what we're saying is there's 10 cubic meters per second divided up among 4 meters of width. So the flow per unit width is 2.5 cubic meters per second per meter of width. And then the critical depth y sub c, we can only use this when conditions are, it's rectangular channel. So it's going to be the flow per unit width, 2.5 meters squared per second. And square that divided by 9.81 meters per second squared. And then take the 1/3 power of that. So 2.5 squared divided by 9.81 and the 1/3 power, it again gives you the depth of 0.860 meters. So you can find the critical depth either according to like the full-blown formula that'll work for any kind of a shape. But a lot of time, these problems that you're going to solve assumes a rectangular geometry, and so then if it's rectangular geometry, you can use the simplified approach where it's based on the flow per unit width. All right. One last thing I wanted to tell you about is that you can sometimes face problems where they're asking you to determine the critical slope. And the critical slope is just how steep does it need to be to cause critical flow depth. And so this would be a combination of both the formula for critical geometry and also Manning's equation. So in this case, they would tell you what is the flow rate, the side slopes, the bottom width, and so you can use all those geometric parameters to set up Manning's equation. What you're trying to solve for is the slope that's going to give you the depth that corresponds to critical conditions. And so you'd start off, it's a two-step thing. First of all, we'd have to use the full version of the critical equation. We couldn't use this rectangular simplification that we just found. So you solve for the critical depth with this formula, and then you put that critical depth into Manning's equation, and I'll just briefly show you what the solution looks like for this one, where you're finding the critical slope. So we know the area formula from that factor table. We've got the wetted perimeter, the W term, and everything. So with the critical depth equation, you can find this is the depth that corresponds to critical. This is the depth that's critical. And then you rearrange Manning's equation for the slope. And so you'll solve for that special how steep the channel has to be in order to cause the critical depth. I'm sorry we didn't have enough time to actually calculate through that one, but hopefully you at least get the idea. So the next thing that you've got is homework number 9 on Thursday. Let me know if you have any problems getting Bentley water gems installed. I'll see you in class on Thursday.